Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Mathematical Relations. Make sure that you are an active learner as you watch this video. We start with a whole bunch of definitions. A relation from one set to another can be thought of as a table that lists elements of the first set and how they relate to elements of a second set. So here we have students and courses. And you can see these are the students and these are the courses that they're enrolled in. So this motivates the following technical math definition. A binary relation, R, from a set X to a set Y, is a subset of the Cartesian product X cross Y. That's capital X cross capital Y. If X, Y is an element of R, then we write X, R, Y, and we say that X is related to Y. If X is equal to Y, we call R a binary relation on X. Now, a function is a special type of relation, but for each X in X, there's exactly one Y in Y, such that XY is an element of F. That's not the case in this relationship, because you can see that Bill is taking both computer science and art, and Beth is taking history and computer science, and so on and so forth. A relation can be listed as a set of ordered pairs that defines a relationship, but another way is to draw what's called a digraph. Digraph stands for directed graph. There's a direction. So here we go from 2 to 2. The arrow indicates the direction. So to draw the digraph of a relation on a set X, we first draw dots or vertices to represent the elements of X, and here we've drawn this same relationship here. And next, if the element xy is in the relation, we draw an arrow called a directed edge from x to y. And so we've connected the things. Notice that if you have an element where x is related to x, for example, 1 is related to 1 here, we start at 1 and we have a loop going there, and that is called a loop. And there is a loop at every vertex in this particular example. We define several properties that relations may have. We say a relation is reflexive if XX, an element of R, for every X in capital X. Now, this means that a relation R is not reflexive if there exists an X, an element of capital X, such that XX is not in R. We say a relation is symmetric if, for all XY that are in capital X, if XY is in R, then YX is in R. And here are some logic definitions of those. But in words, a relation is not symmetric if there exists X and Y such that XY is in R and YX is not in R. Again, you can do this by counterexample. We say a relation R on a set X is antisymmetric if, for all xy, an element of capital X, if xy is an element of R, then yx is an element of R. And this was and. If xy is an element of R and yx is an element of R, that forces x to be equal to y. And so that is the definition of antisymmetric. The equivalent characterization of antisymmetric translates for digraphs as follows. A digraph is antisymmetric. It has the property that between any two distinct vertices, there's at most one directed edge. Notice that the digraph in this relation has at most one directed edge between any two. And so that means between 1 and 4, there's only one directed edge. And you see, but there's another directed edge, but it goes from 1 to 2, and so on and so forth. Okay, and we can write in symbols what these definitions mean. But in words, we can say a relation R is not symmetric if there exists an X and a Y where X does not equal to Y, such that XY and YX are both in R. We're going to do some examples of this soon. We say a relation on a set X is transitive if, for all x, y, z in X, if xy and yz are an element of R, then xz is an element of R. Said another way, if the first is related to the second and the second is related to the third, then the first is related to the third. And here are some logical ways that you can state those same things. And so in words, a relation is not transitive if there exists x, y, and z such that x, y, and yz are in R, but xz is not in R. That would be a counter example. Now, relations can be used to enforce an order on elements of a set. For example, if R is defined in the integers by this, x is less than or equal to y, notice that this is reflexive because x is less than or equal to x. If x is less than or equal to y and y is less than or equal to x, then x equal y. And if the first is less than or equal to the second and the second is less than or equal to the third, then the first is less than or equal to the third. We call that transitive. If you have these three properties, you call it a partial order, and this is the definition of a partial order. Now, it's a partial order rather than a total order, because sometimes there will be things that are not comparable. We'll do some examples of that. But okay, suppose that R is a partial order on a set X. And if X or Y is an element of X, and either X is, and this is kind of a generalization of less than, but X is related to Y, or Y is related to X, we say that they're comparable. And this is talking about the order relative to this. Now, if x and y are elements of x and neither one can be compared, they're incomparable. And if everything is comparable in the set X, we call it a total order. Let's look at an example of this. The less than or equal to relationship on the positive integers is a total order, since if x and y are integers, then either this is less than or equal to x is less than or equal to y, or y is less than or equal to x. But if we talk about a different relation, for example, the relation called divides, and this is dividing evenly on the positive integers, has both comparable and incomparable elements. For example, 2 and 3 are incomparable since 2 does not divide 3 and 3 does not divide 2. But 3 and 6 are comparable because 3 divides 6. Given a relation R from x to y, we may define a relation from y to x by reversing the order of each ordered pair in R. This is called the inverse relationship, and it generalizes what we talked about with inverse functions. And the formal definition is here. So R inverse is equal to the set of yx such that xy is an element of R. And we can also talk about the composition of two relationships. So if we have a relationship R1 from x to y and a relation R2 from y to z, we can form the composition of these relations by applying the first relation R1 and then the relation R2. And this composition of relations generalizes the composition of functions, and the formal definition follows. So if R1 is a relation from x to y and R2 is a relation from y to z, the composition of R1 and R2 denoted the same kind of notation. Composition R2 composed with R1 is a relation from x to z defined by this relation is a set of ordered pairs xz such that xy is an element of R1 and yz an element of R2 for some y, an element of capital Y. Now we're going to continue with some examples of these definitions in 15.1. So I will see you then.